So today we are going to be presenting the yaw, roll, and ride dynamics for my 2013 BMW 335i, also known as Betsy. My name is Jack Harstead.
Hi there, this is Vincent Astorita.
Hi, I'm Ariana.
Hi, I'm Grace Cully.
And hi, I'm Jonathan Todd. The specifications for the vehicle as found on the internet were a length of 182.5 inches, a width of 71.3 inches, height of 56.5 inches, wheelbase of 110.6 inches, center of gravity height of 22.6 inches. The weight is 3,710 pounds. The steering ratio is 15.1 to 1, and the weight distribution is 52.6 to the front or 47.4 to the rear. Starting with yaw dynamics, our understeer gradient we found was 4.333 degrees per G. Our characteristic velocity was 19.0919 meters per second, which came out to 42.707 miles per hour. As you can see, at 10 miles per hour around the turn, we're about 40 degrees. At 20 miles per hour at 47 degrees, and at 30 miles per hour we said that was 60 degrees. And then here's our chart for velocity versus yaw velocity gain.
So for more of the yaw dynamics, we used the K value that we calculated, and assuming a mu value of 1 on the rear, we calculated our front tire mu value to be 0.735. We also calculated our max speed in the 130R turn to be 68.473 miles per hour. Also, in that turn, our steering wheel output was 66.777 degrees, and the weight over the front tire at harsh braking is 73%. This is over 20% higher than the static front weight bias. So for the roll dynamics, the first thing we calculated was the static rollover threshold, and for this we got 1.381 Gs, which is pretty average for either a regular car or even a sports car. For the front ride rate, we got 26,491.6, and for the rear ride rate, we got 36,793.9. So the front ride rate was smaller than the rear ride rate. We think this could just be error in our numbers, or possibly because of using 60% for the weight sitting on the car. So then for the front roll stiffness, we got 33,318.48, which is 41.86%, and the rear we got 46,275.66, which is 58%. And again, we think this is possibly due to error. The front is considerably smaller than the rear, and it should be 5 to 10% higher. So for the roll gradient, we got 6.82 degrees per G. This is a pretty average number for a regular car, even right on the cusp of a sports car. So the car could possibly be improved by adding an anti-roll bar to make the front stiffer. And our numbers are kind of off because we have a higher weight distribution on the front versus the rear, so the front really should be a higher percentage than the rear.
So from our bounce test, we got a total of 25 bounces in the front, which we found to be a natural frequency value of 1.66 hertz. And in the rear, we got a total of 29 bounces, which we found to have the natural frequency value of 1.93 hertz. This could be compared to our calculated natural frequency values, which we found to be 1.26 in the front and 1.49 hertz in the rear.
My name is Jack, and I'm going to be talking about my car's front suspension and rear suspension. So the front suspension of the BMW 335 is a modified McPherson strut design with a upper and lower control arm. So BMW calls this the double pivot front axle design, and this allows it for a more precise steering control and maintain the wheel to be properly aligned and reduce unsprung weight for a more focus on handling. Reasons for implementing this design is McPherson struts are a low-cost option when manufacturing, and considering The 3 Series is one of the most produced cars. It makes sense to put them in there. This also allows for space for the engine and other components as well. As you can see from the engine picture, the components over there are pretty tight, so space is going to be needed. The 2 orange arrows point to where the coil springs can be adjusted, and the car also has shock absorbers to help with its semi-comfortable ride. The ride is a little bit harsh, which makes sense since it is a sportier car. So for the rear suspension, it has a multi-link suspension setup with 5 rear control arms and shocks on each side. This is also common in sportier cars as well, since it's more focused on performance. More links allow for suspension motion and load to be spread over a larger area, and this will help with handling and responsiveness. And in addition, this design also allows for improved traction to keep the rear wheels planted under the road under hard acceleration and under slippery conditions. This is important since even though this car is all-wheel drive, it is a rear bias car. And the shocks also help with the ride comfort as well. But as we saw with the natural frequencies, they are on the higher side, which means a rougher ride.
Okay, so for this slide, this shows the spreadsheet used for the inputs and outputs over the course of this project. The green sections shown are the measured inputs for every value, while the orange section shows the measured outputs. Each of these cells show the appropriate estimations over the course of the project for the yaw dynamics, the roll dynamics, and the ride dynamics. The first section here shows the lateral acceleration for each input, then the understeer gradients given by the slope of the acceleration and the tire degree angle, then the characteristic velocity, and then the yaw velocity going down for each input. Then the front mu value under the assumption that the tires are 1.0 tires, well, the back ones anyways, and then the estimation of the maximum speed allowed for the 130 radius turn, as well as the lateral acceleration, tire angle output, steering wheel output, and then the weight over the front tire at hard braking. For the roll dynamics, static rollover threshold, ride rates, and stiffness. Each of those are shown below, and then down below shows the natural frequencies compared to the calculated ones to the measured ones. And that's just about it. And here they are near the bottom in hertz.